Okay, hi everybody. So problems 1 through 4, I wrote out solutions. For problem 5, let's look at that. The fundamental theorem of algebra, just go to the Wikipedia page and just, I guess, memorize what it says. It's easier to memorize it when you understand what it means. So then for part B, I'll just give you a hint for part B. Multiply this by the number 4 plus 3i, and just look at what you get. And then try to make it degree 5. Okay? So by hint, I don't mean that it's now easy, like you know what to do now. What I mean is pause the video, and it'll take some thought until you figure out how to do this problem. Okay. Problem 6. What is a sequence of complex numbers precisely? It's a map. So a sequence of complex numbers is well, at this point I might as well just... A sequence of complex numbers is a map from the natural numbers to the complex numbers, okay? You can give that map a name if you want, and we'll do that in part B. But this is what it is. It's a map. It's for every natural number. By the way, this set is the set 0, 1, 2, 3, 4, 5, forever. It's an infinite set. And so when we map this set into the complex numbers, we are choosing infinitely many complex numbers. 3 gets a complex number, 4 gets a complex number, 5 gets a complex number. We usually write those z sub 3, z sub 4, z sub 5. But let's talk about that in the next part. Explain at least 3 different notations for sequences. Okay, so for part B, one notation is to write n, and then this is the maps to symbol, / maps to in LaTeX. N maps to Zn, and then to give like a formula for each number. And so what this is saying, this is giving us a sequence. So here's one example of a sequence, and in general we would say formula for the nth complex number. Okay, and here's another is to write Zn and then parentheses, and then in our book they say like n greater or equal to 0, or n greater or equal to 1, or n greater than 0. But this always confuses me because that suggests that n is a real number. N is not a real number. The input of our function is the natural numbers, and so I would write something like this. But often in our book, they just leave that off, and they say like this. And here they haven't actually given a formula. So an example, and maybe this would be even better to write like n goes to Zn. An example would be that you would maybe write this. Or an example would be just to write that. And then you just have to guess that this represents a map sending any natural number to a complex number. Okay. What's another notation? Another notation is just to write like Zn equals the formula. And this is very much similar to this one, except this one makes it clear that what we have is a map for every n, and then even better is to write something like for n in the natural numbers, like saying what the input space is. And same thing for here, it would be nice to write for every n a natural number. Okay. And so really, like all these different notations, are there any others that I'm missing? The best notation is to really write out like n maps to c, n goes to 1 over n. You can even give it a name, like you could give this map the name z, and then you could give this a name and call this z sub n. In the computer you would write z underscore n, and it would produce this like subscript. Something like this. This really shows the input space, the output space, and the formula and your notation for each element. Oh, another notation for a sequence is to just write out like 1, 1/2, 1/3, 1/4, 1/5, 1/6, and then at some point you get lazy and you write ... and forever. And so you really only gave us 6 numbers. But what you're intending is for the reader to understand that there's a rule here that makes sense for every number in the future. And that rule is that you send a number to 1 over n in this case. Okay, so I just used the sequence, the harmonic sequence, for my examples in all these cases. All right. This is a vague question. So your answer may look different, but you should just talk about the different notations, and a lot of the things I said in words, like in the audio of this video, you could actually write down in sentences, and that would be nice. Okay. Let's look at problem 7. First of all, let's get rid of this. So problem 7, this is in the book. It has a formula. It's in the book. This one has no formula. So this was an unfair question. I apologize for that. It was meant to make you think a little bit. There is no formula for the nth prime number. Okay, so D, the geometric sequence with fixed parameters A, C, that's in the book. E, the geometric sequence whose elements are roots of the polynomial z of k minus 1. And then the geometric whose elements lie in the unit circle but never repeat. So let me discuss these two. Okay, so first of all, this goes back to the points on a unit circle from problem 4. So if I take this point, well, here, let's draw the unit circle. And let's chop it in. There's 1. And then here is what number? It's cosine 2 pi over 3? Yeah. Plus I sine 2 pi over 3. Okay. And then this number over here, its complex conjugate, is, well, we could just put a minus sign there, and that would be correct. But more helpful is to write cosine 4 pi over 3 plus I sine 4 pi over 3. And so here is a sequence. Take n and send it to cosine of n times 2 pi over 3 plus I sine n times 2 pi over 3. That's a formula for a sequence, so now I've written down a sequence. And in this case, this would work for z to the 3 minus 1, because all this is going to do is just go here, 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 around and around and around those 3 points forever, and it'll all 3 of those are roots of this equation. So if we want zk, then all we do is we just take this bottom number and put a k. Okay. Our sequence will repeat. All these numbers are going to repeat over and over again as we come around. But yeah, so that works. Now this is the answer for part A. The roots of that polynomial. And it's a geometric sequence. Why is it a geometric sequence? Well, because I could have written n to cos 2 pi plus I sine 2 pi over k, all of that raised to the nth power. So now n appears right here and only there, and it just says how many times to multiply, because if I start here and I multiply it, if I square it, I get here. If I cube it, I get here. If I raise it to the 4th, I'm back to where I started. Raise it to the 5th, I'm back over here. And so this shows that it's a geometric, and these two are equal actually. So this sort of shows the geometric sequence part of it. Okay, before the video ends, I'll solve problem 7f, a geometric sequence whose elements lie on the unit circle but never repeat. And so all we have to do is just take this same formula here, but not make it with just a fraction of 2 pi, but rather with an irrational number. So if I send n to cosine of 2 pi times, let's say, the square root of 2 plus I sine 2 pi times the square root of 2, and I raise that to the n. Now I have a geometric sequence which will never repeat, because square root, and no multiple of square root of 2 will ever be some multiple of pi. Okay, that's not super obvious, but you should experiment with that. Another way to do this would be just to take the number 1 and then raise that to the nth power. That gives a geometric sequence, and it will never repeat. Okay, because when you square this, you'll get cos 2 plus I sine 2. When you cube it, you'll get cos 3 times I sine 3.